talking about the parts of the earth where life exists. So when we say words like hydrosphere, you're talking about wherever there is water associated, right, in planet Earth. And so here we're looking for parts of the earth where there is large amounts of life, or things that follow the 5 qualities of life. So in biology, we say that the source of all energy on Earth is the sun. Now, what kind of energy? If we're talking about thermal energy, well, there is something called geothermal energy, and I will write that down because it is significant. Geothermal energy is the heat that actually comes from the Earth's molten core. And so it actually is able to unleash its own heat or use its core as part of a heat source. And that does affect somewhat the life on Earth. However, we could say, though, that all the chemical energy is from the sun, because through the nuclear reactions that are happening with the sun, or sort of the result is the sun of that nuclear fusion reaction between the hydrogen, you get all the elements that the Earth is comprised of. And more importantly, you also get the ability of photosynthesis from the sun. Now, only a very small part of the sun's energy actually comes to the Earth, right? It's distributed amongst all the planets in the solar system, and it radiates throughout space, okay? So a small part of that comes to the Earth, and of that small part, a lot gets reflected. And here, you got the Earth's energy budget. Now, this here, absorbed by land and oceans, this is primarily what we're interested in biology. So I'm going to circle that 51%, and that's really a biological number, okay? And we call that a biological number because from that 51% that gets absorbed, that's where life comes from. So trophic levels refer to the energy hierarchy levels in an ecosystem. And you could say species within the same trophic level occupy the same energy space, right? Or energy relationship, or are the same, or use the same primary sources of energy. And so you can think about 2 distinct trophic levels. You have the autotrophs, which are producers using photosynthesis. So these typically refer to plants. And then you got the heterotrophs, which is anything that eats plants and then, of course, being eaten itself. The other thing that is often present in these trophic levels are something called indicator species. Now, it's mentioned over here, but it's not actually described what it is. So an indicator species, and not all animals inside a food chain level or a trophic level are indicator species. This is particular a species whose absence is going to be felt by the environment. Primary consumers eat producers, right? So often we say that the primary consumers are basically the first consumers above the plant trophic level. So producers we refer to usually as plants, and then the primary consumers are typically herbivores. Now, a lot of people actually get these terms confused when it comes to decomposers versus detrivores. Although they play a similar role in terms of indicator species in their environment, they do quite different things. So what a decomposer does is they're the organisms that are responsible for decaying or breaking down dead matter. And that doesn't mean that they eat them, right? But they simply break them down into smaller, more pure substances and then use those. Detrivores actually consume dead matter. So they're not actually breaking it down, they're consuming it and taking whatever energy is available to them from that dead matter. And so they play a huge part in the nutrient recycling in the forest. Because if we look at, let's say when an organism dies over here, then the decomposers, namely the bacteria and the fungi, well, they break those down and then recycle them back to the soil, which you'll find plants that are able to sprout because now they have this nutrient-rich soil from the decomposers. And then the primary consumers now eat the plants that risen from those patches. And then, of course, the secondary consumers eat often the primary consumers, and in some cases they eat also the producers as well. But so it really starts with a lot of the decomposer. Now, photosynthesis is an endothermic reaction, and what that really means is, see how the energy is on the reactant side? That means that energy is absorbed or consumed. Now, where does it actually get absorbed from? Well, it'll be photo energy or light energy, and that'll be from the sun. Okay, so it's an endothermic process. It absorbs energy. Now, it absorbs energy not as a reactant necessarily, but it's more like a catalyst. Okay, and what a catalyst is that's a compound or some sort of mechanism that speeds up the chemical reaction. Now, in biology, we call these enzymes. All right, speeds up reaction. Otherwise, it could take a really, really long time, or it just won't have enough activation energy to happen at all. Now, aerobic respiration, or cellular respiration, is quite the opposite. You have glucose here that actually gets consumed, so it needs food. So this would be considered a consumer, even though we're talking about small entities like bacteria, etc. And a plant, because it's able to produce its own food, is a producer. Now, one thing I also want to mention is this looks a lot like a combustion reaction, but really what separates it from a combustion reaction is that in cellular respiration or aerobic respiration, the state of water is always liquid, and that's because it occurs in a closed system, which means it doesn't let energy in or out. Okay, so there's nothing added. Now, when it comes to, you could say, a combustion reaction, water is always going to be vapor. Now, often we associate the making of organic compounds by the combustion reactions, but that's not always going to be the case. So once, in terms of the chemical cycle, you have biological decay, and then you got heat that breaks those down into simpler compounds. Once in a while, it's not just the combustion that does it, but these certain organisms that convert your inorganic compounds, and that's usually stuff like carbon solid or carbon dioxide, and they turn them into organic compounds, and that's done without the presence of sunlight. And so when this happens, that's chemosynthesis, right? So you're making it could be sugars, it could be alcohols, all those organic compounds, not through photosynthesis, but through chemosynthesis. Now, the first law of thermodynamics is probably one of the holiest laws in physics, and it's also known as the law of conservation of energy. And it states that energy can either be created or destroyed, but it only transforms from one form to another. And what that really means is if I got 50 joules of energy going into a system, and I write in, then I'm going to have 50 joules of energy going out. Now, that might be in a couple of different forms. You might have some loss to heat. You might have some that it's going to cause something to move. And then you might get more that might get stored in a different way, right? So more stored energy. So again, whatever you start off with, you have to end. So here we write, for example, turning on the light would seem to produce energy. However, it is electrical energy that is converted. Right, so it actually goes from electric potential, right, to photo energy. And then in certain lamps that are not efficient, we sometimes feel thermal energy, right, or the light bulb heat up. And again, that's going to depend on how much electric energy is originally put in. Now, the second law of thermodynamics states that entropy of any isolated system always increases. So here's what I want you to kind of understand. When we say the word entropy, we're more or less talking about chaos, right? So if you think about let's say, particles that seem to be kind of all binded together and they're sort of organized. Over time, they're going to spread out, right, within the container and be less organized and kind of spread out and do their own thing. Now, the number of particles is not going to decrease, right? The amount of energy is always going to be the same. Mass has to be the same as well. But that's what we refer to with energy. Think about it as chaos, or entropy, I should say. So isolated systems spontaneously, that means without energy. So there's a lot of key terms in biology that if you overlook them, you're going to miss the general meaning of things. So without energy added, okay? Evolve towards the state of maximum entropy of the system. So that's a big word. So simply put, the entropy of the universe only increases and never decreases. What that means is, okay, matter and energy move to chaos. Okay, so if things are organized, if you don't put any effort to keep them organized, they're going to descend into chaos. And why? Well, it's just easier to do. So I want you to think about a bookshelf, okay, that has, let's say, 1,000 books placed in it. Okay, now, if you take that bookshelf and you somehow tilt it over, you're still going to have 1,000 books. So the potential, right, the mass of the books didn't change, right? But now ask yourself this. Is it easier to take those 1,000 books and push them off the shelf, or to take those 1,000 books and put them neat and tidy and organized on the shelf? 1,000 books is still 1,000 books, right? The answer is to organize it. So just like the bookshelf would easily descend into chaos, or it's easier to put it into chaos, so is the universe. I want you to think about a room, right, as you wrote over here, right? That if you don't continuously clean your room, even if you put things back over time, right, dust is going to collect and things will start to break down. And so it'll naturally descend into chaos. If this didn't happen, well, we would never clean our houses, right? So then what does this tell us about evolution theory? Well, it tells us that over time, your speciation, or the creation of species and the branching out of species, should increase. That as the world goes or continues, then we should see more creatures evolve over time into different creatures. So as we think about energy moving through an ecosystem, right, we can think about it in accordance with this energy pyramid over here, where you have the greatest amount of energy, okay, at the bottom, and then it decreases as we go to the top, and it actually decreases quite significantly. So the species or trophic level at the top here would have the least amount of energy. Now, the way that it increases, or I should say decreases, as we go up the pyramid, it decreases when we go down the pyramid, all follows the rule of 10%. And what that means is, let's say I have 1,000 joules of energy at the bottom, then only 100 joules of this will get passed off to the top. And of the 100 joules, okay, only 10 joules would get passed off to the level above it. And then finally, only 1 joule would get passed to the front. And so we see that there's a difference of about 1,000 times from the bottom of the pyramid to the top of the pyramid. Now, these biomass indexes here are really just density of the mass per kilometer squares that species occupies. So let's say we were asked to make a 3D pyramid of numbers, okay? And we're giving you the trophic levels over here and the number of organisms in that area that we're building this pyramid for. Well, remember, if it's 3D, that would be something like a cube, right? Or another 3D shape. So cube is the simplest version. And so these numbers, that would be a cubic number. And so if you're going to transfer this to a 2D, the first thing that you're going to do is you're going to take the cube root of these numbers. And what that's going to do is give you the linear or 2D version. So the cube root of 729 is equal to 9. The cube root of 42,875 is 35. And we do the same thing with these numbers. And these are kind of the 2D linear numbers that can represent the 3D space we're trying to communicate here. So then you want to decide on a scale. And when we say decide on a scale, look at your numbers and decide which scale would allow you to fit the biggest number, which in this case would be 35. So it says for these numbers over here, using centimeters and a scale of 1 to 2 is probably a good idea. And what we mean by that is that 1 centimeter is equal to 2 organisms. Okay, that way you're not going to have something that is longer than, 17 centimeters long in this case. Otherwise, it's just not going to fit on the paper. And I would also bring your paper horizontal. So I'm going to make paper horizontal. And we're mentioning all of this because, again, you have an assignment where this needs to be done on one of them. So we're showing you how to do this. And then once you can put this into a computer program and it'll actually graph this for you, you'll end up with something like this, where this pertains to the biggest mass, right, of the second trophic level. And then it's going to scale it for you. And what you're seeing here is really the impact that each of these trophic levels have. Lastly, what we want to say today is that people are a part of the food web, and they're actually a huge part of the food web. So as a species that takes food, right, we tend to kind of eat them all, right? We eat primary, secondary, and in some cases, tertiary consumers, right? We talk about the balanced diet, especially nowadays with the carnivore diet. People who adopt the carnivore diet would spend a lot of the times in this realm of the food chain. And so people also use part of the food chain for secondary needs like firewood, building materials, clothing, right? So a lot of this stuff comes from your organic processes. So we rely a lot on organic compounds in order to make these things as well. If you look at clothing, esters are really just another type of organic compounds, the same that make the perfumes and the plastics. And so we tend to use a lot of our resources from bio-rich places like the tropical rainforest. And so the key question that we want to ask ourselves is, how do we measure when we're taking too much?